All right, class. This is Unit 4. Unit 4 covers quite a bit of material and is probably the most difficult unit in the course. We cover two of the most difficult topics in Unit 4. So confidence intervals and hypothesis testing. So confidence intervals play a major role in all of those statistics that we see on TV, where it states 48% plus or minus 3% favored a certain candidate or topic. This week, you'll be introduced to confidence intervals for large and small samples. You'll learn how to perform calculations for large and small samples and how to construct confidence intervals for proportions. Additionally, we'll learn about hypothesis testing. Hypothesis testing is an extremely important part of statistics. According to Wolfram's Math World 2014, hypothesis testing is depicted as the tool of statistics used to determine the likelihood that a given hypothesis is true. When performing a hypothesis test, sample data is used to test some claim about the population. So hypothesis testing is basically in any science, we test hypotheses, right? So in chemistry, if you're trying to prove that certain things happen, you will actually perform an experiment. And that's what we do in statistics when we're doing hypothesis testing. Hypothesis testing normally consists of 4 steps: formulating the null and alternative hypothesis. The null hypothesis is the hypothesis being tested and is either accepted or rejected. Identifying the test statistic that can be used to test the truth of the null hypothesis. In this class, we just use 2. Computing the p-value, and the p-value is defined as the probability of drawing the sample being tested given that the null hypothesis is true, and then comparing that p-value to an accepted significance value. So this week, you'll be introduced to hypothesis testing for the sample mean in situations where the standard deviation is known and when it is unknown, and you'll learn how to perform hypothesis testing for population proportions. Right, we won't test claims about the variance and standard deviation. I need to ask them to update this. So confidence, we will construct confidence intervals for the mean when the standard deviation is known and unknown. We'll perform hypothesis tests for the mean for one sample where the standard deviation is known or unknown. And we will not perform hypothesis tests for 2 samples. So we only do these first 2. Okay, so let's go ahead. Well, first of all, confidence intervals are covered in chapter 6. We'll be covering section 6.1 and 6.2, confidence intervals for mean of large samples and confidence intervals for mean of small samples. And then in chapter 7, hypothesis testing, we'll only be doing chapter 7. We don't cover chapter 8 in this course. Hypothesis testing with 1 sample, and we'll cover sections 1, 2, and 3 of chapter 7. So let's go ahead and get started with chapter 6, confidence intervals. So chapter 6, again, we're covering section 6.1 and 6.2. So section 6.1 are confidence intervals for the mean when we know the standard deviation. So I just want to be clear, we rarely ever know the standard deviation. If we knew the standard deviation for the population, we would also know the mean. So sometimes we'll take a sample and we'll calculate a standard deviation and we'll use that, but this in practice doesn't really happen. It happens, I guess, if we had old data, like say we had data, say you're looking at housing prices and you had population data from 10 years ago, then you calculated the variance even though the prices might change, so the mean changes over time, we might expect for this standard deviation to stay the same. And so then we could say that sigma is known. But like I said, in general, this is not the case. Right, so we start by calculating a point estimate for our population mean mu. And all a point estimate is a single value estimate for a population parameter. And the most unbiased point estimate of the population mean is the sample mean. So we're trying to estimate the population parameter mu, and we estimate that using the sample statistic X bar. So X bar is a point estimate for mu because this is one single point. So it's a single value estimate. This is a single value. An interval estimate is an interval or range of values used to estimate a population parameter. So we start with our point estimate, and then we create an interval around that point estimate. And how confident do we want to be that the interval estimate contains the population mean? So this is how we determine the level of confidence. So basically, we're going to start with our point estimate, and then we're going to create an interval around that estimate. And notice this interval is symmetric. Okay, so this value is X bar minus some number, and this is X bar plus that same number. So the way that it works is we start by deciding what our level of confidence is, and we call that C. And the probability that the interval estimate contains the population parameter is C. So this is the level of confidence that we pick. And so C is the area under the standard normal curve between two critical values. Okay, so the way that it works is this level of confidence, say it's 95%, then this area here would be 95% from negative ZC to positive ZC, which means that this area out here is 1 minus C, or 5%, divided by 2. So this would be 0.025, and this would be 0.025, and this area would be 0.95. Okay, and then we look this up in the standard normal table. So this value would be, we would use the norm.inv, and we would put in as our probability 0.025. And to get this one, we would use norm.inv, and we would put in our probability, the 0.025 plus the 95, or 0.975. And so that's where these two numbers come from. And this one will give me, because of symmetry, this one will give me a negative z-score. This one will give me a positive z-score. But the absolute value of these is the same. So basically, once I look up this one, which is the easier one to do, right, we just take 1 minus C and divide it by 2. And then once we look up this one is just the absolute value of this, because it's going to give me a negative z-score. So here it's showing us what it looks like for the 90% confidence interval. So I'm just going to go through the whole thing again to help you understand. So here, this area with a 90% confidence interval, this area here in the middle is 90% is 0.9. So this area is 0.9, and which means that this area is 0.1 divided by 2, or 0.05. This area is also 0.05. So when I look up this z-score, I would use norm.inv, and I would put in 0.05. So let's actually do that just to show you that that works. Let me grab my Excel spreadsheet. Okay, and let's add on chapter 6. Okay, and I want to make this bigger so you can see it. Okay, so chapter 6 is confidence intervals. So let's start by looking at this one. So I just want to get this ZC. So our confidence level is 90%. Okay, so that is 0.9, right? And then, so I'm going to look up Z. So Z, so the negative Z Okay, so the negative Z for the 90% confidence level would be equal norm. I'm going to just use my arrow key to go down, norm.inv, and you can tell you're using the right one because this returns the inverse normal distribution for us for, oh, we want the S, sorry, this one. For z-score, returns the inverse normal cumulative distribution for a mean 0 and standard deviation 1. Okay, so we put in norm.s.inv and then our probability 0.9. Oops, my bad. We want the area in the tail. Okay, equal norm.s. Okay, hit the tab button and that'll grab that. And then the probability that we want is this value, 1 minus this. I'm going to put that in parentheses, 1 minus this value, right? 1 minus C divided by 2. Be sure you put this part in parentheses, the 1 minus 0.9. Otherwise, it'll go 1 minus 0.9 over 2, and it'll use 1 minus 0.45. Okay, so first of all, here, let's do this. The area and the tail. I'm going to just calculate it so we make sure we got it right. So this one is 1 minus C divided by 2. Okay, so that should be 0.05. And now our negative Z C. So this one is going to be equal norm dot S dot INV 4.05. Okay, so that gives me the negative negative 1.645, and then the ZC is the absolute value of this one. Okay, so I could also look up 0.95, right? Because this area is 0.5, this area is 0.95, but I can just use the absolute value of that one. So that's where those came from. And the sampling error is the difference between the point estimate and the actual population parameter. So for mu, the sampling error is the difference between X bar and mu, but mu is unknown. So mu is unknown and X bar varies from sample to sample, right? So I take one sample and I calculate the mean, and if I take another sample and calculate the mean, I'll get a different X bar for each sample. So the margin of error is the greatest possible distance between the point estimate and the value of the parameter it is estimating for a given level of confidence. So again, it's basically the maximum error X bar minus mu that we would get for that particular level of confidence. So the way that we calculate this is the error equals ZC times sigma of X bar, and sigma of X bar is sigma divided by the square root of n. So I just want to go ahead and put these formulas in my Excel spreadsheet. Okay, so this is the margin of error. Okay, and the margin of error is denoted by capital E. So E equals ZC times sigma X, which equals ZC, and this is our ZC here, ZC times sigma divided by the square root of n. Okay, so we take ZC, we multiply that by, let's put that in brackets to make it a little easier to see, sigma over the square root of n. Right, this is called also the maximum error of the estimate or the error tolerance, but we're just going to call it in this class margin of error. But you might see this in a paper or something called the maximum error or the estimate of error tolerance. Right. So the way that we calculate the confidence interval for the population mean is we will calculate our X bar, and then the C confidence interval for the population mean is X bar minus the error to X bar plus the error. So again, the error term is the margin of error is ZC times sigma over the square root of n. And the 90% confidence interval for the population mean, remember that ZC for the 90% confidence interval was 1.645. So I would use 1.645 here and multiply that by sigma over the square root of n to get my error. And then I would take my mean minus the error to get the lower bound of the confidence interval, and my mean plus the error to get the upper bound of the confidence interval. And the probability that the confidence interval contains the mean mu is C, assuming that the estimation process is repeated a large number of times. So let's go ahead and add this also into our Excel spreadsheet. Okay, so the confidence interval is the way we normally write it is it's X bar minus E and X bar as an interval. The way we write an interval is with a comma. I don't like how they wrote this because we don't know that the mean is actually in this interval. Okay, what we do know is this part here. The probability that the confidence interval contains the mean is 90%, assuming the estimation process is completed a large number of times. So this is what we actually know. Okay, this is what we know. So we actually do not know for sure that this is true. So I don't like how your textbook wrote this. So the way that we construct a confidence interval for the mean is we will first, verify that n is greater than or equal to 30, or that the standard deviation of the population is known, and we have a normally distributed population. Okay, and then we have to do that in order to use the normal distribution. We learned that in the last chapter. And then we will find the sample statistics, n, that's our sample size, and x bar. And we find x bar by using the sum of x over n, or in Excel, you just use the average, right? The average formula will calculate this. And then if sigma is known, we're going to use sigma. Otherwise, if n is greater than or equal to 30, we can find the sample standard deviation S and use it as an estimate for sigma. So remember the sample standard deviation, we use this formula. And in Excel, you're just going to want to pick the standard deviation and then dot S for sample, dot P is for population. Okay, and then you can find the critical value using table 4. This is from the appendix in the back of your textbook, table 4, or we use Excel. I'll always use Excel to do it. So we find the ZC that corresponds to a given level of confidence. And then from that, we can now find the margin of error using this formula. So we put in our ZC from the table or from norm.inv, and we multiply that by sigma divided by the square root of n. And then the left endpoint of the interval is x bar minus e, and the right endpoint is x bar plus e. And then finally, we interpret the results. So remember that mu is a fixed number. So it is either in that confidence interval or it is not in that confidence interval. The problem is that we don't know what mu is, so we don't know if it's in the interval or not. So it is incorrect to say that there is a 90% probability that the actual mean is in the interval, because the probability it's in this interval is either 0 or 1. What is correct to say is if a large number of samples is collected and a confidence interval is created for each sample, approximately 90% of the intervals will contain the mean. And what does that mean? So here, the horizontal segments represent confidence intervals for different samples of the same size. So basically, we took so we started with a population, we took a sample of size n, we calculated x bar, right? And then we created a confidence interval. And then we took another sample and we calculated x bar. This one happened to be exactly the mean. And then we created a confidence interval. And we did it again and again and again. So we repeated it n times. So we took 10 samples, we took 10 samples of size n. We created 90% confidence intervals. So we used that ZC. And what we would find is that 10% of them would contain the mean. 90% of them will contain the mean, and 10% of them will not contain the mean. So here's our actual mean. It's contained inside of 10% of the sample, or 90% of the samples, or 9 samples, and one of them does not contain the mean. So this is why when we interpret it, we don't say that there's a 90% probability that the actual mean is in the interval. What we'll say is with 90% confidence, the mean lies in the interval. Okay, so 95% of the intervals contain the mean. So we'll say with 90% confidence. And then given a confidence level and a margin of error, the minimum sample size needed to estimate the population mean is n equals z times sigma over e, and take that whole thing and square it. So we use this like they just did a bunch of vaccine trials, and they had to calculate how many people they needed to give the vaccine to in order to see if the vaccine is effective. And this is when you would use this formula to calculate what n you actually need. So what is the minimum sample size needed to estimate the population mean? And if sigma is unknown, we would estimate it using S, provided we have a preliminary sample with at least 30 members. right? So that's the end of this section. And now we are able to do the homework number 1 through 6. So let me open that up. Oh, this is giving my grade. That's okay. I was worried that I opened it and it was showing a student's grade. All right, so let me put that back over here. So let me go into the assignment. So we're going to start with Unit 4, Assignment 1. All right, so we want to find the critical value necessary to form a confidence level, an interval for the confidence level shown below. So we want to find ZC for C is 0.95. So here they gave me a C value. So this is the level of confidence. Let me add in here that this is also called C. Okay. So if, man thinks that that's a copyright, okay, let me just put in comma. Okay, so that's C. Okay, there's a level of confidence C. So if I make the C 0.95, this is set up to calculate it for me. So ZC is going to be 1.95996. And they want this to 2 decimal places. So there we go, 1.96. And now they want us to use the values on this number line to find the sampling error. So remember the sampling error. I don't think I put that in here. The margin of error. So let me add a row. So to add a row, I'm going to click here. I right clicked and then I can click insert and I can add a row. So I'm going to add a row for the sampling error. Okay, and the sampling error is X bar minus mu. Okay, so if they give me an X bar and a mu, my sampling error given X bar, let me insert a couple more rows. So let me insert, I want to put in X bar, mu, and the sampling error. So I'm going to go ahead and go insert and here, insert up. Cancel that. Let me go home. And if I click here and I go insert sheet rows, I can insert 3 rows here. So I'll put in X bar. I'll put in my mean and then my sampling error. Okay, so my X bar is 4.9. So up here, let me make that red. All we put in here is this number. You guys know how to do change percentages. I'm just going to move that over. All we put in to get the Z score is the C, the confidence level. And then here, I'm going to put in X bar and the mean, 5.46. Okay, so I put both of these in. And then my sampling error is equal X bar minus mu. So my sampling error here is negative 0.56. Okay, and that's another one of the same. Okay, now we're going to construct a confidence interval for the population mean. So to construct a confidence interval for the population mean, we need C, X bar, sigma, and N. So we haven't done this part yet. So I'm going to add in here. Construct confidence interval. I abbreviate that CI for mu. Okay, so we're going to start by putting in C, X, whoops, X bar, sigma, and N. Okay, so C is 0.95, X bar is 4.5, sigma is 0.7, and N is 45. Okay, these are all inputs. All right, and then remember to calculate my confidence interval. I put it down here. It's X bar minus E to X bar plus E. So the first thing I need to do is calculate E. So before I can calculate E, I need this part here, right? I need to calculate ZC. I'm going to copy that down. Okay, but I'm going to change this. The area in the left tail is going to equal 1 minus the confidence level divided by 2. Okay, so the area in the left tail is 0.025, and here is my Z, right? And then I need ZC, okay? And then my E is sigma X bar, which is sigma over the square root of N times ZC. So my E is this. I'm going to use just the second part of the formula. Okay, so for E, I'm going to go equals, oh, that's why it was taking up extra space. The double equal sign in there. Okay, so equals ZC, this, times sigma divided by the square root of N. Okay, so be sure you do my problem with me, and then you can go do your own. Okay, so ZC times sigma over the square root of N is 0.204. So this is my error. And then I'm going to calculate my confidence interval in 2 pieces. So I'm going to calculate my lower CI, so the lower one, and the upper. This is like my lower bound of the confidence interval, and this is my upper bound of the confidence interval. Okay, so my lower one is X bar minus E, X bar minus E, oops, E, and my upper one, X bar plus E. So my confidence interval goes from 4.29 to 4. Well, it's actually going to be 4.3. Let me make these 2 decimal places. Okay, so it goes from 4.3 to 4.7. Okay, use the confidence interval to find the margin of error and the sample mean. So remember, the confidence interval is from X bar minus the error to X bar plus the error. So they first want us to find the margin of error. So let's go back. Let's see. Go back here to my looking for the, so weird. I was trying to find the picture. I don't know if I accidentally closed the I must have accidentally closed the presentation. Okay, just bear with me. I'm going to open it back up. Okay, so here we are back in module 4 overview. Let me just open the presentation back up. I did not mean to close that. All right, so what I wanted to do is show you from this picture because it's just easier to see it. Here, sorry, don't want to make you dizzy. Here, when we're looking at this. So remember, this is the left endpoint is X bar minus an error. The right endpoint is X bar plus an error, which means this distance from here to here is E, right? From, so if I take X bar minus this, I get E, and this distance is also E. So from here to here is 2E. So if I subtract the lower bound from the upper bound and divide by 2, I'll get back the error. So again, this is the error plus the E plus E, right? So if I subtract these and divide by 2, I'll get back the error. All right, so let's go back in and look at that homework. So now they gave us, so the confidence interval, I'm going to put it in as two pieces, 1.5 to 1.96. Okay. So to get E, so the first thing I want to know is what is E? So E is going to be the upper CI minus the lower bound of the confidence interval divided by 2, right? Because the distance between these two is the error times 2. So E equals this. Oops. The upper bound of the confidence interval minus the lower bound of the confidence interval divided by 2. All right. So the way that we get that is equals parentheses this one minus this value divided by 2. Okay, so my error is 0.23. All right, and then it wants to know what is the mean. Okay, what is the sample mean? So let's look at this picture again. The sample mean is in between these 2 points, so it's the average of these. Right, it's right in the middle, so it's the average. So the sample mean X bar the upper confidence interval plus lower bound of the confidence interval divided by 2. So that's how I would get the average. Okay, or I can use average equals AVERAGE. So there are 2 ways I can do it. So I can add these together and divide by 2, or I can just average them. So my sample mean is 1.73. All right, and then the last question from section 6.1, construct a 90% confidence interval for the mean. And now they are giving us words. So again, we already did this part, right? We calculated that here. So now we can just do the same thing again. So I'm just going to copy this part here. So I did Control C and then Control V, and this is going to be number 6. So they want us to construct a 90% confidence interval for the population mean, right? And then they should give us all the other pieces. You are given a sample mean and a population standard deviation. Use the information to construct a 90 and 95% confidence interval for the population mean, and then interpret the results. Okay, so a random sample of 55 home theater systems, that's my N, has a mean price of 139. So that's my mean, X bar. Assume the population standard deviation is 18.3. That's my sigma. So they gave me the confidence level, the mean, the sample mean, the population standard deviation, and the sample size. And now you notice that this all works for me. So the area in the left tail is 0.5. Z is 1.645. It's actually going to round to 1.645. And then our E is ZC times sigma over the square root of N. So we can just check that. So it's using ZC times sigma divided by the square root of N. And then my lower bound is X bar minus E. And my upper bound is X bar plus E. And again, I just double click this so I can see the formulas. So my confidence interval is 134.94 to 143.06. And then it has me construct a 95% confidence interval. So all I have to do is change this to 0.95. My formulas should all work. And it is 134.16 to 143.84. Okay, and then it's going to say to interpret it. So with 90% confidence, it can be said that the sample mean price lies in the interval, in the first interval, and with 95% confidence, it can be said that the sample mean price lies in the second interval. Okay, or is it with 90% confidence, it can be said the population mean lies in the first interval? Or is it with 90% confidence, it can be said, all right, so first of all, is it the sample mean that lies in the interval or the population mean that lies in the interval? So I just want to go back here and we're going to look. A confidence interval says, so it's the confidence interval for the population mean. Okay, so first of all, we're using it to estimate a population parameter. So the confidence interval is for mu. We're creating a confidence interval for mu. Secondly, we know that the population mean lies in the interval. It definitely lies in the interval because the interval is constructed around it. So this part doesn't make any sense to say that it can be said with 90% confidence that the sample mean lies in the interval. It can be said with 100% confidence that the sample mean lies in the interval because the interval is constructed around this. So the first part is the population mean. And then the second part is asking us which is wider. So what happens is when we draw these intervals, the more confident we want to be, the wider the interval will become. Thinking it would show us, but I guess if we look here, the wider the interval would become because Z gets bigger, right? So if I make this 95%, my Z gets bigger and I'm multiplying Z by a number, so the wider that this interval becomes. So the 95% confidence interval is going to be wider than the 90% confidence interval. And if we look, it's wider. So you look at the 95%, this number's less, this number's greater. So this one is wider than the 90. All right, so that is the end of section 6.1.